We're going to take a look now at unit number 3, which will be covering constant one-dimensional acceleration as well as free fall. Now, constant one-dimensional acceleration, this is where the velocity changes linearly with respect to time. So if we were to draw a graph, what we find here is that the acceleration versus time graph, where the motion begins just before time equals 0, and once we hit time equals 0, the object starts to accelerate. And it accelerates in a constant rate, which is a horizontal line. Now this is given that the acceleration begins at time equals 0, which you can see in the graph on the left. Now if we were to draw a velocity versus time graph that is based off the acceleration versus time graph, this is what it's going to look like. So first of all, just before we hit the origin, it is also a constant horizontal motion until it meets v0, which is the y-intercept. And then once we begin acceleration, we have a positive slope for the velocity. We can find the change in velocity by integrating a dt, which is actually the area under the acceleration with respect to time graph. If we perform this integration, what we find is v minus v0, which is equal to at, which is one of the very important formulas that we'll be using in this course. Now, if we were to derive the graph for the displacement versus time, this is what it's going to look like. So we have a decreasing displacement, and then once it reaches a positive velocity, we begin to see that rise in displacement. The formula for the change in displacement is equal to the integral of v dt, which is actually just the area under the velocity time graph. Now, if we perform this integration by substituting in v equals v0 plus at, what we have is this formula down here, which is x minus x0 equals v0 t plus half at squared, where v0 is equal to the velocity when the acceleration began, and x0 is the position when the acceleration begins. Now that is using calculus. What if we wanted to use algebra? This is how we do it. So we know that the acceleration is constant, and we also know it is equal to dv over dt. Now, since it's constant, we know that the average acceleration is equal to the instantaneous acceleration. So therefore, acceleration equals vf minus v0 over t minus 0. And here is a graph that can represent this type of constant acceleration motion. Then, what we can derive this formula is that Vf, using the formula above, we can derive Vf equals V0 plus At, where the velocity changes linearly with time. Now, to get the displacement in the same time interval, what we have to do is to find the area under the velocity time graph. And we can do that either manually or we can use methods of integration. So one of the formulas for delta x, which is the change in displacement, is the integral of v dt. Another way of writing this, it is the average velocity times the time. We know that the average velocity, if you think about finding the average of two numbers, which is the initial velocity and the final velocity, all we have to do is just to add up those two values and divide by 2. So if we do that substitution, we have half v0 plus vf times t, where vf is equal to v0 plus at, which we derived earlier. So therefore, delta x is equal to half v0 plus at multiplied by at. And if we simplify that, we get v0 t plus half at squared. Or this can be written as x is equal to x0 plus v0 t plus half at squared, where we can see that the displacement changes with t squared. Also remember that the average velocity, which we have shown above, is equal to half v0 plus vf. Now, if we were to use the formula Vf minus V naught is equal to AT, as well as delta x is equal to the average velocity times t, then the time can be eliminated, and now we have Vf minus V naught is equal to acceleration times the change in displacement divided by half V naught plus Vf. Or this can be written as Vf squared minus V naught squared is equal to 2a delta x. So if a question doesn't involve the time, then you can use this equation to help solve that problem. Now let's take a look at an example of constant acceleration. Example number 1 says that a car goes from 0 to 60 kilometers per hour in 6.0 seconds. And we are asked to find how far did it go in that time. We can use the formula delta x is equal to the average velocity times time, which is equal to half of the initial velocity, which is 0, plus the final velocity, which is 60 kilometers per hour, multiplied by 6.0 s, and then we can use the unit conversion of 1 hour divided by 3,600 seconds to get 0.05 kilometers. Number 2 tells us that a car accelerates for 5 seconds at an acceleration of 4.0 meters per second squared, and we need to find what the final speed is as well as its displacement. We can use the formula Vf is equal to V naught plus AT, where the initial velocity is 0, the acceleration is 4, the time is 5. So now we have 20 meters per second as our final answer. Now we can find the displacement, which is delta x is equal to the average velocity times time. And this is equal to half of the initial, which is 0, plus 20, which is the final velocity, and multiply by 5, and we get 50 meters. There's also another way of finding it. We can use the formula delta x is equal to half AT squared, which is equal to half of 4 meters per second squared, multiplied by 5 second, all squared, which would give us an answer of 50 meters. Number 3, we have a car which accelerates from 30 miles per hour to 80 miles per hour while covering a distance of 800 feet. Calculate its acceleration in meters per second squared. Now the formula we're going to use is acceleration is equal to Vf squared minus V naught squared over 2 delta x, but we need to do some conversions first. So 30 miles per hour, we need to convert this to meters per second, and what we can do is we can multiply it by 1,609 meters in 1 mile, and then multiply again by 1 hour, which is 3,600 seconds, and what we get is 13.41 meters per second. 80 miles per hour, we need to convert that as well to meters per second, so that is multiplying by 1,609 meters divided by 1 mile, multiply again by 1 hour divided by 3,600 seconds, we get 35.76 meters per second. Also, we have to convert 800 feet to meters, so we multiply it by 0.3048 meters in 1 foot. This gives us 243.8 meters. We can now find the acceleration. Acceleration is equal to the final velocity, 35.76 all squared, minus the initial velocity, which is 13.41 all squared, divided by 2 times 243.8, which gives us 2.25. Now, how long did this acceleration take? Well, we can use this formula Vf equals V naught plus AT, where the time is equal to Vf minus V naught over A. So if we put in all the numbers, we should get a time of 9.93 seconds. Another way is to use the formula delta x is equal to the average velocity times time, where time is equal to delta x over V average. And if we plug in all those numbers in, we also get the same time of 9.93. So this last part here is just an extra step, but we have already answered the acceleration, which is 2.25 meters per second squared. Now the last thing we're going to take a look at is free fall, which is also considered to be constant acceleration. Now when dealing with problems involving free fall, which is when an object is released and there are no other forces acting on it except for gravity, we can use the constant acceleration formulas that we have already seen. And there are some times where you may want to use the y-axis. So therefore, we can say that the acceleration will act downward. So always remember that you have to first outline which direction is positive and which is negative. So let's say the going up is positive y and going down is going to be negative y. So therefore, since we're accelerating downwards, therefore the acceleration due to gravity is negative g, which is equal to negative 9.81 meters per second squared. This means that if we are converting to y, we can write the new equations of motions as y equals y naught plus v naught t minus half gt squared. Vf is equal to v naught minus gt. Vf squared minus v naught squared is equal to negative 2g delta y, where g is equal to positive 9.81 meters per second squared. So just take note that the negative is already taken into account in these equations, so therefore we can just use the positive value for g. For example, if we drop a ball from a tower, at time 0 seconds, the velocity will be 0, average velocity will be 0, and delta y will be 0. At time 1 second, velocity will be negative 9.8 meters per second, average velocity will be negative 4.9 meters per second, and delta y will be negative 4.9. At 2 seconds, the velocity will be negative 19.6 meters per second, average velocity will be negative 9.8, and the change in displacement will be negative 19.6. At 3 seconds, negative 29.4 is the velocity, average velocity is negative 14.7, and delta y is negative 44.1, and so on and so forth. There is the values for 4 second and 5 second, which you can also copy as well. Now let's take a look at one final example. Let's say we throw a ball upwards at a speed of 25 meters per second, which is also our initial speed. And the question asks us, how high does it go? We can use the formula V is equal to V naught minus GT, where the peak is when V final, or just V, is equal to 0. And this is where it reaches the peak and it begins to reverse its direction. So at the peak, we know that T is equal to V naught minus V over G, and this, substituting in the values of 25 minus 0 divided by 9.81, gives us a time of 2.55 seconds. Now the average velocity until the peak was V average equal half of 0 plus 25, which is equal to 12.5 meters per second. So the vertical displacement was delta y is equal to V average T, which is equal to 12.5 times 2.55, which gives us a vertical displacement of 31.8 meters. There's also another way you can solve this, which is using the formula delta y is equal to Vf squared minus V naught squared divided by negative 2g. This is going to be equal to 0 minus 25 squared over 2 times 9.81, which is equal to 31.8 meters as well. So that is the end of unit number 3.